I'm a mechanical engineer, tech lead at Meta, and I'm here with Sébastien Lafond, who's an engineering manager at Danfoss. And I just want to acknowledge Grace Piety, one of the thermal engineers at Meta, who helped put a lot of the work here on the thermal side together and did a lot of testing, so she was not able to make it. We're going to go over the Orv3 blind mate interfaces group, and this is kind of unique in that this group is not just developing valves, we're developing manifold interfaces and fundamental designs. We're developing the interfaces on the frame that we're kind of talked about in HPR a little bit in terms of where the manifold mates, as well as IT gear concepts to help, and along with interfaces to help develop a holistic solution to have blind mate liquid connections for IT gear. So the group is quite diverse. We have the work streams there that I kind of just talked to a little bit, and you can kind of see a bit more detail. We also are working on hose and tubing solutions, but we have valve design suppliers. We have Ratal was key in this in terms of the rack side of things, and we also have suppliers that make valves. WeWin was part of this in terms of developing the IT gear concepts, so it's been a big collaborative effort, as well as manifold suppliers. So I'm going to go over the concept. So we take a basic Orv3 frame and we add a bolt-on kit that basically creates interfaces and stiffeners for the manifolds and the frame to overcome some of the loads. The manifolds are at the rear corners, at the left and right. And the IT gear contains the plug side of the valves, and the manifolds contain the socket side of the valves. And again, all the connections are at the back. And the valves are designed to self-align when you push the chassis in and mate with the manifolds. So we've got a little bit more detailed view on the lower left there. You've got a kind of a transparent manifold with the green socket and the plug that's sitting in there kind of nested inside the chassis. So I'll kind of walk through the basics of each of the parts of the valve design. So the socket on the lower left there is designed to thread into the manifold, and it features an ISO thread interface with an EPDM seal to create a leak-free connection. And the plug valves mount to a chassis with that gray panel nut. And the right side of the plug there on the floating body has a barb fitting to connect to internal tubing that we'll show a little bit more detail later. So this video here shows the initial mating when the valves are aligned, and the second one here shows when there's a radial-only offset, you'll see the floating body adjusts, and then once it's demated, it self-centers, and then the last cycle here is a combination of angle and radial. So all of the capabilities in adjusting for misalignment are within that cup. There's no additional features or add-on adapters. That's the design. And it's designed to allow for a large allowable misalignment and working range. So there's some images down here. At the bottom, it shows a 5mm radial and a combined 5mm and 2.7 degree angle. And then we use the term stroke, almost like a connector for connector wipe. And we have 93.4 to 82.9 working range. So that's 10.5mm of range. And the reasons why that is fairly large is we want to prevent loads on the manifolds due to tolerances. This rack has a lot of tolerances, the gear has lots of tolerances, and also to deal with deflections and things along the line from the loads from the springs and the fluids. We're also developed a blind mate manifold. We're going to be putting out a base specification, which will provide the interfaces and key information, utilizes standard tubing, and all the critical interfaces are machined to maintain precise tolerances. So things like where it mounts to the rack and where the valve spot face interface is for the socket to connect. And they all interface with the liquid cooling kit that was mentioned earlier. And one of the key requirements for the manifolds is also as a structural element to counteract the forces from the fluids and the springs within the valves. And then on the far right there, there's options for top and bottom connections with different types of adapters. And we also developed the blind mate IT gear concept. The key here is it's a concept. The goal here was to develop some mechanisms and the injectors as well as the interfaces that people can leverage, and this will be shared, the CAD for this will be shared when the spec is published. But this particular design, for example, is a 3.0 U high. Doesn't have to be this height, and there's some flexibility in terms of valve locations, in terms of vertical locations, as well as manifold locations. So this is a concept, so people understand this. You don't have to design this exact form factor. Again, the plug valves mount to the rear, and inside the chassis, there's convoluted PTFE tubing that goes from the back of the barb to internal connections within the chassis. Some of the key updates since what we shared in the Global Summit: we increased the working pressure from 35 to 50 PSI. The demate and mate forces obviously had to adjust for that because of the higher pressures create higher forces. So we're going to be updating the curves that we shared, preliminary curves we shared back in the fall to account for that. The valve flow performance and variation met performance targets with same supplier and mixed supplier, and you're going to hear this theme throughout the presentation. A big part of this is about interoperability, right? We want the valves to all work together within a certain performance range so that you can expect, whether it be forces or flow rates, you can have some consistent performance. We did testing at the rack level to the higher flow rates. We actually have bought new equipment with higher capability pumps to support that. We made some minor design changes on a couple of the suppliers. We found some issues during testing, but follow-up regression testing resolved all that. And the vast majority of the rack testing is done. We have a few low-risk climatic tests to get done, and then we kicked off a 1OU feasibility study. I'm going to hand off to Sébastien, and he's going to talk about testing.
Thank you, Glenn. So I'm Sébastien Lafond. I'm the engineering director for the connector business unit in Danfoss. And I'm going to talk about all the tests that we've been doing to ensure the community that we provide a very reliable solution in terms of interoperability. So when you think about it, there are different combinations possible. So 4 different suppliers, 2 different valve halves. So 4 into 2 equals 16 possibilities in terms of configuration. So we also have a big list of tests that we have performed. So in terms of interoperability, 21 tests, so 16 times 21 times 4 different suppliers, it's more than 1,800 tests that has been performed. So a lot of effort has been put into ensuring the community that we are bringing a reliable solution. Also, what we did is that we worked on the requirement, on the testing requirement, because we figured out that testing something which was pretty new for all of us in 4 different plants, 4 different companies, we were not testing exactly the same way. So we also defined fixture and testing requirement so that we are sure that we all test the same way. So there are still some tests which are remaining, as Glenn was mentioning, but almost everything was done, so we are almost completed. And based on the last update from the OCP summit in San Jose, the force curve was updated based on the higher working pressure. So as said, everything is 90% completed, and on early May we'll provide the full study. Some very important tests are obviously the pressure drop tests that were done. So a lot of efforts again. All those 16 configuration with all the different mating distance, 5 mating distance in the 4 different plants is also more than 3,000 data points that were collected to ensure that all the pressure drops with all the different combination are within a plus or minus 10%, which is a great result. So the design allows for some variations and also the testing. So everything is within this 10%. The slight variation in the valve should be accommodated by the cold plate loop, as this has a higher contribution. Some more details on the testing. So, as far as the maximum working pressure, as mentioned, we increased it from 35 psi to 50 psi. Glenn was mentioning that there are some climate tests which are pending. Those are pretty low risk. 2 of the 4 sites needs to complete this, but it will be done very soon. Then there are some pretty standards tests like spillage, air inclusion, burst coupled, uncoupled. So the safety factor here for the burst test is 3.5, and everything passed. The last test is the O-ring blowout. So what is O-ring blowout? O-ring blowout is when you connect, there is a risk that the O-ring, which is at the valve position, escape from its place. So we need to make sure that when we connect at the maximum working pressure to the drain, then the O-ring stays in its position, and that's what we did, and everything passed. Then some other tests like the maximum flow rate. So we already talked about the pressure drops. So everything passed. Operating temperature, non-operating temperature. That's where we need to finalize some testing. Salt spray, humidity testing, everything passed. And then there is the bulk of all the effort that we did, and the reason why we had to do multiple design iterations is really to ensure that when we do connection, disconnection at different speeds with the different position that Glenn was mentioning, aligned, radial offset, radial plus angle, with all of those different position, plus all of the different 16 combination, plus different speeds, static 40 millimeters per second, 310 millimeters per second. With all of those situations, wet and dry, we wanted that there is no binding, that we stays within the force curve that we defined in the spec. And then here finally, everybody passed the test, which was a great success for all of us, and this was really the bulk of our work so far. I give it to Glenn for the right level testing.
Thank you. So we did extensive amount of testing, as you saw in the valves, but we also did rack level testing, so I'm going to walk you through those. We did a shipping and distribution test. You can see on the right here, that's a rack in its shipping container, and we tested this full of fluid and ran it through its paces, and that passed. We also did mate cycle testing, which I'll get to in a minute. We have a slide that covers that, and as well as safety and flow rate distribution. We're going to get into that as well in more detail. This is a high-level summary. So we had done the testing in previous builds, but not at the 50 psi. So we ran that, and we also made the temperature at its highest temperature that we're speccing it at, which is 60 C, with the idea that that creates the most coefficient of thermal expansion on the manifold. So this is, in a sense, a worst case. We did chassis mate cycles for 50 cycles, and those chassis had same supplier and mixed supplier to kind of get a good feel. We looked at all the locations, so we got a good feel between if the type of valve supplier mattered or the location in the rack. We found consistent results. And as in previous testing, we did see the forces start to rise over time. However, the forces were 20% lower as compared to the last time, and were within spec. In terms of safety, we passed hydrostatic, which is 3 times the max working pressure of 50. We did a temperature cycle creep resistance test where you condition the rack for 87 degrees for 14 days, and then go back and run that same test, and we passed that. And then we also did a mechanical pull force test, as well as an evaluation of the tubing materials, and that passed based on evaluations of the specs by our safety engineer. I'm going to get here into flow performance testing. We had a setup with manifolds and blind mate valves in the chassis, and we fitted the chassis with orifices to simulate expected flow impedance for a cold plate. We measured pressure and flow rate to understand the manifold and performance, and you can see that simple diagram on the right here that shows the chassis with the valves and the various pressure sensors along with the orifice and then a flow meter within that same chassis. So the goals, we were to achieve higher flow rates up to 90 LPM per valve and up from the 4 that we were before. You might remember earlier in the discussion, I talked about how we ordered new equipment with higher capability pumps. That's how we're able to run this. We also looked at blind mate valve mixing and chassis configurations in terms of impact on flow, basic locations within the rack, that type of stuff. And the goal was plus or minus 10%. And then we also wanted to determine the impact of the top versus bottom valve LQD inlet for the fluid into the rack and out. And then we did a performance comparison between the different manifold suppliers, because the manifold designs have subtle differences in terms of cross-section. There's some freedom in that in terms of the specs, so we wanted to verify that those would be similar. Major takeaways. We saw 8 to 9% variation with a full chassis, 12 chassis setup. And we were within the 10% goal. And the rack configurations with lower chassis counts actually had slightly lower variation. And then the top exit LQD versus bottom exit LQD found to have similar variations, so there's no concerns there based on our results. And then the two suppliers, Parker and Invent, their manifolds are found to have similar flow variation and pressure drop as well. So it's all good stuff. So what are we planning on doing here as far as publishing? We're going to be publishing a blind mate valve specification, a blind mate manifold base specification, and I want to clarify here, it's a base specification, just like the Orv3 frame base specification. It's to build off of. It's not a specific exact part number type design you would order. And then we're also updating the meta frame spec with a whole section that details at the rack level blind mate considerations and details on the design. We're also updating the IT Gear V3 design guide with a blind mate section as well. So quite a bit there. So what's next? We need to get those tests done that we talked about, the environmental tests. And then we need to finish up the various specifications and guidelines, and we're planning on reviewing on the cold plate call on May 8th, so it's a little less than 2 weeks from now. And hopefully pending the steering committee approval, we plan on publishing them by the end of June. And in addition to that, the suppliers are going to work to get their specific designs reviewed and placed on the OCP marketplace. So what's next? We're in the process of, now that we've kind of got all the key tests done on the fixtures, we're going to start looking at alternate routing, hose routing studies. And what that is that's inside the IT gear. We're going to look at different scenarios and routing and terminations to kind of give some feedback to the community on what that impact has on best practices. We're also going to complete a 1U feasibility study where we're looking at valve and hose space optimizations to try to get those keep outs down. And we developed a fixture. You kind of see it in the background, kind of transparent there, but we have a optical camera and some pretty cool setups here to kind of look at that as we look at different layouts and optimize that. We're also working with WeWin, developing a 1OU chassis, just like the 3OU one you saw. And then the manifold suppliers are each doing manufacturing capability study on a 1OU pitch. And you say, well, what does that matter? Well, as the valves get closer, and they tend to build up more heat, and you have more of them. So we want to make sure that when the manifold's done, that it meets the requirements that will be called out in the base specification in terms of tolerances and those kinds of things. So how do you get involved? There's some QR codes here for the cooling environments and the cold plate work stream. And we have a monthly call. It's the second Wednesday of each month, and we give updates in there on a regular basis. And we'd love to have you join us and get more involved. Any questions? Yes, sir. So it's going to have all that. All those are going to have that information, right? We're not releasing an IT gear you should go buy. We're giving you the interfaces and the requirements. there's flexibility innate in what we're trying to do here. We don't want to, even like the inlets and outlets, you saw those large QDs, that's not a requirement. That's an example implementation, but really the focus is on things like maximum deflection and tolerances and interfaces to give as much freedom to the community and potential developers as possible. Yes? That's not, respectfully, that's not part of this. That's more maybe the HPR we talked about earlier. It's not really in the scope of this. Yep. Yes. They're stainless. The valves fundamentally are stainless with EPDM seals, at least for the wetted surfaces, to clarify. Yes. No, because of the innate nature of this thing being able to adapt and adjust for misalignment, there were some concerns there about, in fact, initially on in early prototypes, we dealt with a bit of galling and wear. So that already showed there's some sensitivity there. And as we optimize the design, it would not have made sense to look at that. We did think about it, but it wasn't really a viable option in this case. I saw another hand back there. And when the spec's released, we'll talk about that. We give some guidance, and really one of the key parameters is coefficient of thermal expansion, right? Because part of the development of the spec was accounting for that. So you've got a 2+ meter manifold, and as it gets hot, it wants to expand, right? So we do call out in the spec, you'll see when it's released, we do call out a maximum CTE, and then you can decide structurally and otherwise what works for you. But we do have some requirements on what those need to be as far as the different grades. I don't remember them exactly offhand. I'm sorry, I didn't catch the last part. Yeah, so the focus here was doing the testing that you all would have asked. But for your, say you're going to implement a real system, you'll have to do your own testing, right? These are about evaluating the components to have confidence that they'll meet that. Okay? That's it. Okay, thank you.